in your recording, and our next speaker is G.Borot. Oh, here we see. So the next speaker is G.Borot, who will talk about n equal to 2 supersymmetric gauge theories and topological recursion. Please.
Are you muted, Gator?
It seems you are muted.
Okay, so now I can repeat that. I would like to thank all the organizers in Moscow for organizing this and also inviting me to talk. So I will talk about a joint recent work with Vincent Bouchard and Thomas Kreutzig in Edmonton, and as well as Nitin Chidambaram in Bonn. So this is in this archive paper. And the work is about relating, doing computations in n equal 2 gauge theories using topological recursion. And the summary, if you don't want to stay for too long, is that there are W constraints for the partition function in gauge theory. And here one consider for the pure gauge theory. Also, you could also do insert matter. And these are solved by the topological recursion. And maybe this recursion is actually not exactly the one of Chekhov and Arontin, but a non-commutative version of it, which has also partly been studied before by Leonid, Bertrand, Olivier, Marshall, etc. And the purpose of my talk is to explain more in detail what does that mean and what does that do. There is a precursor to this work, although we don't use the same language. I should mention that there's a work of Hénard and Béliard a couple of years ago, who study what they call TODA and conformal field theories. So it's a 2D CFT with W algebra symmetries. And what they do is they take some assumptions on the correlation functions, which are motivated by what you expect this to satisfy it. And under these assumptions, they solve the word identities using TR or non-commutative version of it. So what we do in this work is somehow a bit more general. I will explain in which sense. But at the end, you obtain, in a special case, similar formulas. Good. Since I'm talking about gauge theories, I have to explain a little bit what mathematically I want to study. So I will start with a short reminder on gauge theories. So first, let's just consider the Young-Mills. So nothing super yet. Just a Young-Mills theory on a 4-dimensional compact manifold. Typically, I will take the 4-sphere. And let's say that you start with gauge group SUR, although a good deal of what I'm going to say has a generalization to simply lay gauge group and even a bit more. So in the physics, on the physics side, what you would like to do is to compute the path integral where the weight is given by the Young-Mills action. So you integrate over all G connections on M4, and the action, so there's this G is a coupling constant, and the action is trace of the square of the curvature. So that's what you want to do at the quantum level. So in order to make sense of that, first you look at the classical solutions, so the critical points of this action. And this is described by the anti-self-dual connections. So here the star is the Hodge star. M4 is a Riemannian compact manifold. So anti-self-dual connections. And you want, of course, this is a gauge theory, so you want to consider that up to gauge transformations. That is, you can change A to gamma A, gamma inverse plus gamma inverse d gamma, where gamma is a group valued function on M4. And so in gauge theory in particular, one wants to study those connections, some of which have finite, I mean, you could say compact support, or that are localized in a region, in a finite region of the space. And these are called instantons. And once you have such a connection, you can define the instanton number, D, which is, so it's an index. So you can compute it in this way. And it is an integer whose signs depend whether you're in the self-dual or anti-self-dual case. So classically, you would get a contribution from, I mean, the value of this action on such a classical solution, which will be exponential of -8 pi squared over G squared, and then the absolute value of D. But this is only the classical aspect. So what happens when you want to consider supersymmetric gauge theory is that you not only have the gauge field, but you also have some fermions, some other fields. So lambda will be fermions, phi will be some other scalar field. And then you would have the Young-Mills action, plus also coupling between the connection, the fermions, and the scalar field. And this is supersymmetric. So in 4D, you would consider, what I want to consider here is there's two supersymmetry with charge which are preserved. And what's interesting about this is that when you have more symmetry, the computations are easier, at least on the physics side. And this integral can be reduced. I mean, you can argue that it can be reduced to doing an integral over the classical phase space. And that would be the moduli space of classical solutions. And this is because fluctuations of fermions, that's what physicists have argued, cancel fluctuations of gauge fields. So somehow the semi-classical approximation is going to be exact. So I want to come closer to what does that mean for mathematicians. So here, when one can study the classical algebraic geometry of this space of classical solutions, I can mention a classical result of Donaldson. Let's say that if you look at anti-self-dual connections, so SUR on S4 with a trivialization at infinity, so that's a certain point on S4, when you see it as a one-point compactification of R4. Modulo gauge, and with fixed instanton number. So this space is homomorphic to a space which involves algebraic geometry. So which is easier to tackle, which is algebraic SLRC bundles. Essentially, you complexify everything. On P2, there's also a trivialization on the line at infinity. And second Chern number for this bundle, which is D. And this was later generalized for other gauge group. So one thing that we want to do is to consider this theory, but in an equivariant setting. So inside the P2, there would be a C2, and you can consider the action of a two-dimensional torus. So which sends Z1, Z2 to lambda epsilon 1, Z1, mu epsilon 2, Z2. And epsilon 1, epsilon 2 are going to be some complex parameter. So you have this action. Actually, you could say here, I just look at the diagonal torus, but this isn't, you have an action of GL2, taking Z1, Z2 as a complex two-dimensional vector. And you also have this principal SLR bundle. So you also have an action of the Cartan torus. Or let's say you would like also to look at a theory which is G equivariant. So inside here, you're going to take the U1 to the R minus 1. And so this I can describe as an action of U1R, but the charges, because on SL, the charges will go, the sum will be equal to 0. And so what we want to do is a theory which is equivariant for this group, which is GL2C cross SLR. C. Okay. So I said that in principle, you can reduce integral that you want to do for these partition functions to integrals over the space of classical solutions. But the thing is that this thing is an affine space. It's not compact. And one reason is that you can shrink instantons to just be localized at points. And that's one of the source of non-compactness. So here, there's various ways to handle that. One is to replace algebraic bundles by the moduli space of torsion-free sheaves with some conditions. Then you can actually compactify that space. And there's another way, and that's the way I'm going to go, is that if you first add this possibility of shrinking instantons, so this, let me call that bun G, D. So you can do bun G, D prime, and then you just remember where did you shrink instanton. So you have a points defined up to order, so symmetric power of D minus D prime points in C2. And this is still not compact, but it will be enough. So it's called the Uhlenbeck space. And this space has a nice stratification. Which is such that you can consider, so I said you wanted to integrate over these certain things over this moduli space. So somehow you have to consider a cohomology classes to integrate. That's what you would do in algebraic geometry. So what mathematically you have to specify exactly which intersection theory you use. I mean, this space is a bit singular. So here you can consider intersection cohomology with respect to the nice stratification I didn't explain. And here you will look at the equivariant intersection cohomology of that space. And let's call that H D. So now mathematically, the question of doing this integral, one can reformulate that to give it a concrete meaning. In fact, there is a fundamental class inside this space. And one can then consider a generating series for this. So lambda R, let's say lambda, here I put the dual Coxeter number. So in my case here, this is R minus 1, D, 1D. So that belongs to the sum, or let's say the product of this. Okay, perhaps I can do just the sum. And then I add my formal parameter, lambda. So this can be defined. And then the instanton partition function, which is also called the Nekrasov partition function, would be defined as the intersection, as the norm for the intersection pairing inside this cohomology ring of this G. So the different D don't talk to each other. So what I have is lambda to the 2 dual Coxeter number D, and then the intersection pairing of this fundamental class. And that's what we really want to compute. And it's going to depend on all the equivariant parameters that we have. So this vector here, it's called the Gayotto vector. And so when we take the norm, we get the partition function. And so this is counting instantons. And if we compare to the original thing, what we would like to do here is there's the classical action on an instanton that plays a role. And it was this exponential minus 8 pi squared over G squared. So here I have to identify lambda is related to the coupling constant. Well, there's maybe a question of H. Good. And if I come back to the physics, so there's many ways to approach this Nekrasov partition function. One way, which is also one can get that from the 5D n=1 supersymmetric gauge theory by taking a 4D limit. And in that case, the epsilon1, epsilon2 describe what is called the omega background. So some of you may already have heard about that. But I'm not going to say much more. Good. So there's a general relation that was proposed by Aldai, Gayuta, and Tachikawa between these gauge theories and conformal blocks either of the Virasoro algebra or of the W algebras. So between gauge theory in 4D and CFT. And what I'm going to talk now is there's a mathematical incarnation to this AGT conjecture. So it's a theorem which takes the form which I want to explain, because that was the starting point of this work. So here I'm going to move to the group which is rather GLR. The only effect, if I want SLR, is that my charges, so I have R of them, I should just say that they sum up to 0. So it's not much of a difference. And it extends partially to what I will say mathematically extends in some cases for a simply laced gauge group, and also some non-simply laced, but simple complex gauge group. So to talk about W algebras, I need first to introduce the Heisenberg algebra, or it's called sometimes the free boson algebra, for the Lie algebra GLR. So this has fields indexed by 1 R, that correspond to the roots of GL, to the simple roots of GLR. And these fields have such an expansion. So that's the primary fields. This Heisenberg algebra is actually a VOA generated by those fields. And Heisenberg means that you impose the following commutation, these modes satisfy the following commutation relation. So it's diagonal in the A's. That's in fact the killing form between the simple roots. A indexing an orthonormal basis of the simple roots. Here you have M delta M plus M prime 0. And here it will be convenient for me to add an H bar. And I will specify its role in the theory later. So it's well known that this has a representation in the bosonic Fock space. So this is sometimes called the Sugawara construction, or the free field representation. So V, this bosonic Fock space here, represented in the following way. So it's the formal functions in countably many variables. M here is positive, and we also add a formal parameter H bar square root. And so here inside there's the constant function 1, which I want to represent as the vacuum. this bosonic Fock space. And the representation, so you have to, what you mean by representation, that there are operators which act as differential operators on this V, which have this commutation relation. And so there's an obvious way to do that, that for the positive modes, you just differentiate with respect to TMA. For the negative modes, you just multiply by the variable itself. And then the zero modes, because of this factor, they commute to everything. So you can set them to be equal to some scalars. And here, the scalar that is relevant to what we want to do is this one. So it's expressed in terms of the equivariant parameters of the gauge theory. And so with this, one can introduce the WGLR algebra. So the principal one. So if I was doing that for WSL2, that would just be the Virasoro algebra. For WSL3, that's the algebra introduced by Zamolodchikov in '83. And in general, it was studied in particular by Fagin and Frankel at the end of the '80s. And more recently, I think in mathematics, it was proved by Arakawa and Molev. I think it was in 16 or around this date. But this was known in physics way before. That this, so it's a VOA, which is generated, strongly generated. So in physics language means that there are primary fields, which are the WIM, the M plus I. So I is between 1 and R, is the conformal wave, or the spin, if you want. And so these fields defined by the quantum Mira transform so that dates back to the work of Fatayev and Lukyanov. And these are defined in terms of the Heisenberg fields. So you take WIZ, and here you form a differential operator with respect to the Z variable here. And this generating series is the product of Heisenberg modes. And is ordered from A equal 1 to R. So this is a differential operator with respect to Z, whose coefficients are the Heisenberg modes, these J's. And once you write this differential operator in Z in a normal ordered form with putting all the derivatives to the right, so this guy will have to commute to this J, so there's going to be J's and derivatives of J's. You find the field generating the W algebra. That's one of the description known of this W algebra. And here my alpha 0 is epsilon 1 plus epsilon 2. And so now we have the tools to formulate the theorem, which is due, so in some version, to Schiffman and Vassereau. Also, they didn't use intersection cohomology, they rather used Borel-Moore homology, but it is a result of a similar flavor. For GLR, it was generalized by Breverman, Nakajima. I think it's around 12. This is around 15. And Finkelberg. Good. And so this theorem is saying that first, this sum of the Hg, so this intersection cohomology summed over all instanton numbers of this moduli space of instanton with exactly d instantons. This is isomorphic to the bosonic Fock space, and it admits therefore representation of WGLR with, so here I have this H bar and I have to specify it. So this is minus epsilon1 times epsilon2. The second part is that the Gayotto vector is determined by the following equations. So you take the positive modes and then you find 0 unless I is equal to R and M is equal to 1. And in that case, you see a lambda, lambda R. Lambda R or lambda, not just lambda. That's for I from 1 to R and M positive. Good. And this is, so if I had 0 on this side, that would be a highest weight vector. Here I don't have 0, it's rather an eigenvector of these modes with this eigenvalue, and it's called the Whittaker vector. And the last part, which one needs to compute the partition function, because that's the norm of this Gayotto vector, is a description, I mean, the intersection pairing on that space, which is now identified with the bosonic Fock space, is uniquely specified by the fact that the vacuum vector is orthonormal, and the adjoint for the pairing of these Heisenberg modes is related to the negative modes, to the mode with opposite index. And that allows to compute completely the pairing in terms of the bosonic Fock space. Okay. So these are W constraints. They are for the Gayotto vector, and then one has to take the norm. And it is these equations I want to start with to show that they're solved by topological recursion. Are there any questions so far? That was some other introduction to the topic. If not, let's move. I will talk about array structures that were mentioned in Jörn's talk, because that's the bridge between these W constraints and the topological recursion. And so this array structure were introduced by Kontsevich and Zolbermann around 17. Then they were also studied further in a paper with Jan, with Leonia, and with Nicolas Orentin shortly after. And then there were more with the co-authors I mentioned at the beginning of this talk. So what is an array structure? I will just do it for the ones based on the bosonic Fock space. So we want to introduce the space of differential operators. And then formal series in H bar. So we with the usual Leibniz commutation relation between these. So it's differential operators on this infinite dimensional vector space V. And we can make it a graded algebra by saying that the degree of TMA is 1, the degree of H bar is 2. And therefore, the degree of H bar d TMA, that should have degree -1, degree 2. So that's also degree 1. And an array structure on V is the data of a collection of differential operators indexed by the basis of V. So again, A between 1 and R and M positive, such that we have the degree condition telling us that HMA, this is GMA, so this is H bar d TMA plus something of higher order. So that's higher degree. So in degree 1, there's just derivatives. There's no degree 0. And then there could be terms of any degree. And then there's a subalgebra condition. So they tell us that HMA is a perturbation of the trivial vector fields, the trivial differential operators. And the subalgebra condition means that these operators are compatible with one another. So when you commute the two, that has to be in the left ideal generated by the H's. And this condition is quite non-trivial to address. And the relevance of this is the Kontsevich-Zolbermann theorem, which tells you that there exists a unique, so given an array structure, there exists a unique common solution to all these unique function which is killed by all these operators. So there's unique F, which I will write in this way. So here the G could be a half integer and is an integer which is positive. And we look for solutions of this form. So it's a formal function. So here these FGN, A's, K's are the Taylor coefficients. And here I see TA1, K1, TAN, KN. And this condition means that you only have, this is degree 1, so that makes degree n. That makes degree 2G minus 2, so I only want positive degree. And then we want that the HAM kill exponential of F. So the degree condition actually is responsible for uniqueness. And the existence is because we have this compatibility of these differential equations. If you take an arbitrary family of PDEs, and there's not going to be a common solution, but because you have compatibility, so it's a kind of holonomicity condition, it is possible that it exists. And then these FGNs, if you just write down what is this differential equation exactly, is obtained by the topological recursion, so which is a recursion on 2G minus 2 plus n, just following from these things. Good. So that's the general theory. Now we want to apply it to compute the Gayotto vector. So here I can take WIM, and I'm saying that WIM up to taking linear combinations if the QAs are pairwise distinct, form an array structure. So we've seen here that by construction, they're expressed in terms of these Heisenberg mode, which are either derivatives or multiplication by a variable. So these are elements in the algebra of differential operators. And what I'm saying is that it satisfies the degree condition that one has to compute in using this Mira transform. One can compute explicitly this WIZ. So the degree condition is just a computation, it's not hard. And the subalgebra condition, this is something coming from the theory of VOA. So that's where you really use CFT. It can be proved.
May I ask a question?
Yes.
Whether we are able to reconstruct the original subalgebra from the function f?
Somehow, not generically, yes, I think this is true, but there could be some very specific things which in different subalgebra that lead to the same partition function.
Yeah, okay. Of course, if f is identically zero, then the subalgebra. But generically, it's true. Yeah.
Generically, I think this is true.
Mm-hmm.
If you
Thanks.
sit for an afternoon, I think one can prove that.
Mm-hmm.
So this fact that it satisfies the subalgebra condition for that particular set of modes, it's come from the fact that the subalgebra condition is true when you look, when you only take the positive modes in the VOA. This is true. However, the partition function is just the trivial partition function. So it's not interesting. So somehow this partition function, it's an element of the Fock space, and so it's the vacuum vector. But what we want to get the Gayotto vector is not exactly the WMI, it's rather WIM minus this constant. Minus, so let's say that first I try to remove a constant. And I know this forms an array structure. What about this? So we have two things to check. First, the degree 1 condition. If we add a constant, we can still satisfy the degree 1 condition provided this constant has degree bigger or equal to 2. So here you at least need to put some power of h bar bigger than 1, because then that has the right degree. So you need this, okay. And then what about the subalgebra condition? Well, this is going to be still preserved. So of course, when we shift the h, this operated by a constant, it has no effect on the commutator. However, here we change what is the span of these operators. So if there's a set I, the set of IM such that when we commute this, so WJ n, WJ n2, this is not inside the full span, but only inside the span. So for any J1 and 1, J2 and 2. So here it's the one that don't appear. Don't belong to I. Okay, so I prime, M prime. So when you commute two positive modes, you never see on the right-hand side something that contain an element of I, then you can choose lambda IM non-zero for IM in I, so not appearing in right-hand side. Still gives an array structure. And then the partition function is a Whittaker vector. And so our main theorem let's say it's an observation somehow, which is not very hard once you know this, is that this thing minus delta IR delta M1, so these operator with I equal R and M equal 1 don't appear in the right-hand side. You can prove that using representation theory of your W algebra. And here I'm going to shift it by H bar to the R over 2. So R is bigger than 2, so this has degree at least 2. And so somehow if you compare to the theorem, I had set my constant lambda to be equal to lambda tilde times H bar to the R over 2. So this is going to 0. So I'm doing something perturbative in this lambda. That forms an array structure. And so G in this regime is computed by TR. So how am I doing with time? We started a bit late, so is it 10 minutes or just tell me?
Yeah, it's about 10 minutes you do have.
Okay. So we have the Gayotto vector, and now we want to get to the partition function. And so what I can write is as a Gayotto vector. It's exponential of f times 1, and this 1 is the vacuum vector. And what you want to compute, the Nekrasov partition function is the norm. And therefore, the norm is going to be the sandwich of the adjoint of exponential of f times exponential of f between two vacuum vectors. But this adjoint, so that we know how this adjoint is behaving, it just sends a positive mode to a negative mode. So when I look at this f here, I see the times. So these are negative modes of the Heisenberg algebra. So this guy contains negative modes, and so they act non-trivially on the vacuum. And that's the adjoint, so it's going to contain only positive modes, which are just pure derivatives. And because they are pure derivatives, they act by trivially on the vacuum. because this vacuum, you should think of it as the constant function 1. So whenever you act by derivatives on it, you're going to find 0. So this exponential just as the first time, which is 1 plus derivative. So just give the vacuum vector. So this is the adjoint action of exponential of f dagger on exponential of f. And so it's exponential of the little adjoint action, so the iterated commutators of f dagger on exponential of f. And so I can also write it as exponential of the iterated commutator series.
Gaetan,
Yes?
there is no minus f dagger.
Yes, thank you. There's a minus f.
Okay.
So this is 1 plus a series of derivatives, so it's not going, these one don't contribute. Good. So I could continue this computation. I'm just going to give you the result, is that you can write this as exponential of so the free energy, and this free energy is going to take the form of a series with a topological expansion as well. And this FG, it's a sum of Feynman diagrams. So it's two-level graphs, sums over two-level graphs, where at the bottom you have an F, so an F G0 and 0. And here you have F dagger, G1 and 1, etc., GS and S. There's some automorphisms, symmetry factors. And when I look at this picture, you want the sum of the genera plus the Bettin number that's attached to here. So you see that you have loops here in this graph. Must be equal to G. And whenever you see an edge like this, so the F's have some indices, so it's some A1, so this contains positive mode, so it's some A1, K1, and here's some A2 minus K2. The weight of such a thing is delta K1, K2 over K1 delta A1, A2. So the graphical expansion for the partition function. In particular, F0 is the prepotential of the gauge theory. And it can be computed from, so these Fs are obtained by TR, and then you put them into such a sum. So now I just want to mention what's the relation with spectral curves topological recursion, so the Chekhov and Arontin formulation. So basically, when you have these FGNs, so these are formal functions. I mean, the Taylor coefficient of some formal functions. If you replace this, so you're going to make generating series, you replace it by dzi over zi k I plus 1. And so here, what I want to do is I want to define out of these differential forms on a spectral curve. And the spectral curve is a union, so of disks. So CA is a formal disk. Oops. With coordinate Z. And so here you say that if Z belongs to CA, to that copy, you write D0, 0, otherwise you write 0. CAI. And in that way, you obtain omega G and Z1, Zn, which is a meromorphic differential on Cn. And whenever you have an array structure from a VOA, there's a systematic way to translate that into a TR on the spectral curve for the omega Gn defined in this way. So if you let's just do that for R equal 2, then the spectral curve that you find is y minus q1 over x, y minus q2 over x equals 0. If you have general R, you have many factors. And you may notice it's an unramified curve, so it's something unusual in topological recursion. But if you look at the topological recursion formula, actually it still makes sense. You don't have any more local involution, but you have a projection from here to the disk, which forgets in which disk it was. And above each point here, you have a fiber. And so your local involution is just looking at which other points in the fiber of the same point. This is when epsilon1 plus epsilon2 is 0. If you want in general, you find out that actually the spectral curve is rather something like that. So x, x, x. So it's a non-commutative setting. And what it means is that same TR, there's a recursion kernel. It has the same structure as the one in Chekhov and our Rantin, but the recursion kernel is expressed in terms of solutions of, so let's call that y hat psi equal to some right-hand side. And what we show in the paper is that we make this theory as well work for general R. Good. So all what I said here is for lambda perturbative somehow, because I needed to get that to have an array structure. But it's an ongoing work to also get it for finite lambda, which is really what one is interested in gauge theory. And what we find is TR may be non-commutative on the curve, which is given by this. So you open up, and now it's a ramified curve. Or maybe you have a differential equation version of that. And so now here we're back with usual TR. And in particular, you can find, so one nice thing about it that you can prove, so this spectral curve has genus 0, and it's of the type considered in Alexandrov, Alexandrov, Enar, Chapuis, and Harnad. So topological recursion on that curve computes Hurwitz numbers, weights Hurwitz numbers for very specific weights. And in that way, we can reprove something known by very different paths from the work of Witten and then proved by Nekrasov, that the Nekrasov partition function is also a partition function of Weiss-Hurwitz numbers. So in that way, one can close the loop, and I will stop here. Thank you very much.
Thanks, Gaetan. Let's thank the speaker. Very good. Questions, please. Whether John Harnett is present. And
Could I ask a question?
yeah, you're welcome.
Okay, so my question is about this non-commutativity. I guess this is basically because you want omega 1/2, 1, or like you want to introduce the cross-cap dependence in this topological recursion or area structures.
Yeah, so there's two, I would say there's two things. Either you want to do weakly non-commutative. So you see that I have my, so maybe let's start with the quantum Mira transform, which is here. So alpha 0 equals 0, that you have to send at the very end. So first you express the Wi, and then you set alpha 0 equals 0. That's this epsilon 1 equal minus epsilon 2. This leads to something commutative. You don't have derivatives of the J field in the expression for the W fields. And that gives usual topological recursion on this non-ramified spectral curve. Then you can do a certain regime, which is just epsilon 1 plus epsilon 2 is of the order h bar to the half. And so that's weakly commutative. In that case, you indeed introduce half integer genera. You still have TR, but just you have half integer genus and this cross cap that you said. But the truly non-commutative aspect, actually, when you do this half integer, that can be resubbed. It corresponds to just do that finite. So not going to 0. And here you do see truly the non-commutativity. And so everything, the recursion kernel and so on, is expressed in terms of solutions of the differential equation that replaces the spectral curve. And then you don't need any more a half integer genus because you still have integer power of h bar now. But if we're setting alpha 0, this parameter here, so it's appearing here. If you start to insert in there, so it's like a small parameter in front of each derivative. It's a semi-classical limit. If you set that alpha 0 to be h bar a half alpha 0 tilde and expand your FGNs with only integer genus, you're going to get half integer powers of h bar. And that's going to give you what you would have gotten if you didn't start non-commutative, but just this weakly non-commutative thing where you just needed usual TR with half integer genus. So one is a resummation of the other. Mm-hmm. And even though non-commutative is more complicated, it has actually a simpler structure.
Okay, yeah, thank you.
Okay, there is one more question from Piotr Sołkowski.
Hi, guys.
Hi.
I'm not sure if you mentioned that, or maybe I missed it, but the spectral curve that you might obtain, how is it related to Seiberg-Witten curve?
Yes, it's a good question. So I think Seiberg-Witten curve, if I look at this, so the one for finite lambda, I think you wouldn't do that. You would also, so let's call that C. I'm going to call that C Gayotto, because that's, you do TR on that, you compute the Gayotto vector. And the Seiberg-Witten curve, so in the standard theory, from the work of Seiberg and Witten, from the geometry of that, the prepotential also computed by TR on the Seiberg-Witten curve gives you the F0 of the Nekrasov partition function. And the relation between the two is that this is a branch cover of the Gayotto spectral curve.
So your spectral curve is essentially Gayotto curve.
So what we do is TR on this Gayotto curve, which has actually genus 0. And the Seiberg-Witten is a branch cover of that. And so from this theory, we actually expect to be able to reprove that if you do TR on the Seiberg-Witten curve, you can extract the all order topological expansion of the Nekrasov partition function. But it's a further step. That will be in the next paper, I guess.
Okay, thanks. I'm afraid we have to stop here. No further questions. Let's speak Gaetan once again. Let's thank Gaetan once again. And I stop recording. Stop recording.